There's.
All right, turn to page 214 in your textbooks if you would. We want to look at exercise number 14 there at the top of the page. Page 214, exercise number 14. And read this rather short little problem if you would, Quentin.
One side of the equilateral triangle is 16 inches on the altitude.
All right, what do you suppose we should do, Quentin?
Draw an equilateral triangle.
Draw pictures. A big fan of drawing pictures. So on your paper, go and draw, to the best of your ability, something that we will call an equilateral triangle. Again, we don't trust our eyes, so we're going to say it's equilateral regardless of whether or not it really is. And it says that one side is 16 inches. Audrey, thoughts? Which side? The base? Okay, let's call the base 16 inches. Chris, thoughts?
Every single one of them is going to be 16.
Yeah, they're all going to be 16 inches, aren't they? Because equilateral triangle means all sides equal. So it doesn't matter which one. In fact, technically all of them. 16 inches. And it says to find the altitude. Of course, Jamie, when we think altitude, we think...
angle bisector? Or from vertex angle?
Altitude? There's one word altitude means, class. Perpendicular. There we go, she got it. And so we're going to draw the altitude straight down perpendicular. However, in any triangle, altitude means perpendicular. But this isn't just any triangle. This is an equilateral triangle, which means it's also isosceles, right? Because at least two sides equal, which means when I draw the altitude, Ethan, it bisects the base and
Bisects the vertex angle.
it does bisect the vertex angle, which is why when Jamie said bisects the angle, I didn't say no, because it was true, even though that's not what altitude means. But in this case, the altitude will do that. It'll bisect the vertex angle. It'll bisect the base. Now, what's really key here is the fact that it bisects the base, because Genesis, if the entire base is 16 inches, then each piece of the base now must be 8 inches. And so when it says to find the length of the altitude, which we can call x, initially we're like, I don't know how to do it. But when you draw the altitude, class, which means perpendicular, which means right angles, that forms a couple of right triangles. And because I know it bisects the base, I know 1, 2 sides of my right triangle, and I need to find the third side. And anytime we have two sides of a right triangle, we need to find the third side. We should always use the
Identity.
Pythagorean theorem, right? What is the Pythagorean theorem, Genesis? Where we need to remember specifically, Ethan, C is always the
Hypotenuse.
and A and B are always the
Legs.
Okay, of these, x, 8, and 16, which of those is the hypotenuse, Chris?
The hypotenuse would be the 16, the legs.
Good, the 16, because it's across from the right angle. So we're going to put our 16 squared here. And then A and B would be the legs, which of course, Audrey, are the x and the 8. So 16 squared equals x squared plus 8 squared. Of course, if we were being lazy, we wouldn't write 16 squared. We memorized that in the past. We know that's 256. If we had forgotten, maybe because it's been a couple years since algebra, maybe because you only had algebra 1, didn't get the second year of memorizing these, calculator can do that for you. Of course, all of us should know 8 squared. 64 for sure. And then to solve, we need to do what, Quentin? Certainly. And when we do, of course, we get x squared is equal to
192.
got 192 over there. And that's x squared. And 192 doesn't make sense, does it? We can't have sides of 16, 8, and 192. Remember I mentioned before, if it's absurdly large, you know you forgot to take the square root. So, Quentin, let's stay with you. We take the square root of x squared. That, of course, just gives us x. Can I take the square root of 192 evenly? 196, yes, that'd be 14. So this is almost 14. It's like 13.8, 13.9, something like that. Anyone happen to have it on the calculator? Square root of 196?
13.8.
Okay, 13.8. Okay, so I knew it was something like that.
Really? 13.9 because of 8.
0.85. Okay, so it was right in between the two things I said. 13.8, 13.8, 13.85. But we don't do decimals. What are we going to have to do with our radical class? Reduce it. Let's see, squares. Say the squares with me as I write them, class. 4, 9, 16, 25, 36, 49, 64, 81, 100. That's probably enough. Anyone see a square that goes evenly into 192?
49.
Nope. 64.
64, I heard 16, I heard 49. Let's try dividing it by 49. What do we get?
It's not.
It doesn't come in. Okay, how about 64?
It does. 3.
Oh, okay, so this factors into the square root of 64 times 3. By the way, 16 would have worked as well. This works better. And we can take the square root of 64 to get 8 times the square root of 3 inches. And there's the length of our altitude. Questions on this? Questions on this? Now, I want you to notice something. 16, 8, and then 8 times the square root of 3. These numbers have a little bit of a relationship with each other. If you were to start with this number 8, doubled would be the length of this side, of course, because the 8 was obtained by halving an equal side, right? And then 8 times the square root of 3. Think with me for just a moment. Suppose the sides had been, not 16, suppose the sides had been 10 inches. 10 inches. 10 inches. Well, then these two pieces wouldn't be 8 each, class. They would be 5 each, wouldn't they? And so when I go to plug this in, I would say that 10 is the hypotenuse. So I'd say 10 squared equals a squared plus 5 squared. Of course, 10 squared is 5 squared is, I bring the 25 over as a negative, put that with the 100 to get 75 equals a squared. Of course, we take the square root, and you can't take the square root of 75 evenly, but you could factor it and say that a was equal to the square root of
25 and 3.
25 and 3. Or you could take the square root of the 5 to get 5 times the square root of 3. Suppose for a moment this had been something massive. 36. 36. 36. Well, then when you cut it in half, you're going to get 18. 18. So we would say that 36 squared is equal to x squared plus 18 squared. Now, we didn't memorize 36 squared. Somebody find it.
1,296.
Good. 1296 equals x squared plus 18 squared is
324.
324. Of course, we'll subtract the 324 to get somebody
972.
972, and that equals x squared. And we try to take the square root. Of course, we'll factor that down. And interestingly, divide 972 by 3 on your calculator.
324.
324 times 3. And we can take the square root of 324, class, to get 18 times the square root of 3. 16, 8, 8 squared of 3. 10, 5, 5 squared of 3. 36, 18, 18 squared of 3.
It's half times the square root of 3.
It always ends up being half the side times the square root of 3. That's an interesting little memorized fact, isn't it? Now, I want to point something out. In an equilateral triangle, we memorized way back at the beginning of the year that every angle of an equilateral triangle is how many degrees? 60 degrees. 60, 60, 60. But it's been bisected, hasn't it? Into 2 halves, both of which would be 30 degrees. And if we were to take just half of our triangle here, we would have what we call a 30, 60, 90 right triangle. Go to a new page in your class notes section. Go to a new page in the class notes section of your book. At the top of the page, I want you to label it special triangles. Special triangles. Now, there's an infinite number of right triangles you could construct. But one that's special has a double acute angle. 30, 60, 90. And a 30, 60, 90 right triangle is always half of an equilateral triangle. And in a 30, 60, 90 triangle, we said if you were to take the length of one side, don't write this down yet, you would have to cut it in half to get the little bisected piece. And you would take that bisected piece times the square root of 3, right? But I'm lazy, I don't like fractions. So what if instead of starting with x and then having to cut it in half, what if we started with 2x? Because that's easier to cut in half. Half of 2x is
X.
and then when I multiply that by the square root of 3, there's no fractions. And you've seen this on the wall of my classroom all year long. And finally, we're here.
Oh.
This is a memorized relationship. So on your paper, go ahead and draw a triangle, a right triangle, label it 30, 60, 90, and label it just like this, just like what we see on the wall of the classroom. We're going to memorize this relationship of sides. That in a 30, 60, 90 triangle, there is what we call the short leg. Kendall, we miss you. There is also what we call the long leg.
That was anything. Thank you.
Anyway, and then we also have the hypotenuse. Of course, we know the hypotenuse is page 153, the identify bracket. Page 153, the identify. Sorry to leave you sitting there so long. I get caught up in this exciting stuff I'm teaching my students. Of course, we understand the hypotenuse is always across from the right angle. That makes sense. The short leg would, of course, be across from the smallest angle, wouldn't it? But then the bigger acute angle is going to have across from it the longer leg. Now, I do want to point this out. The square root of 3 is approximately 1.7. That's not as big as 2. This is bigger than that. Of course, the hypotenuse has to be the biggest side. A big mistake students will make is they'll look at this and say, oh, little leg, x, twice as big an angle, twice as big a side. No, not twice as big angle, twice as big side. It doesn't work that way, okay? Twice as big side is actually across from the 90-degree angle. But 60 has across from an x times the square root of 3. We need to memorize this fact. Have this in there on a special page of class notes labeled special triangles. But there's another special triangle we want to talk about. It's called the 45, 45, 90 right triangle, sometimes called the isosceles right triangle. Isosceles because two sides are equal. Well, you know in a right triangle, the hypotenuse has to be the biggest side, right? So the hypotenuse can't equal anything else. But the legs could be equal. And so if you had two equal legs, opposite equal sides would be opposite equal angles. Equal angles, equal sides. And since the two acute angles of a right triangle have to be complementary, if two sides are equal, the two legs are equal, then you will get 45-degree angles as the acute angles. And of course, then you would have your hypotenuse, which would be, of course, unequal. Well, for this, we could call the legs whatever we wanted. We could call them, I don't know, 5 and 5, because they would be equal to each other, right? And we don't know the hypotenuse, so maybe we could call that x. Well, don't do this with me on the paper yet, but I would say that hypotenuse squared equals leg squared plus leg squared, which would be that x squared is equal to class 25 plus 25, of course, would be 50, or we could say 25 times 2. Which would be 5 times the square root of 2. But if they were 8 and 8, then it would have been 8 squared and 8 squared, which would be 64, plus 64, which would be 128, which would be 64 times 2, which would be 8 times the square root of 2. Are you starting to catch on to the pattern? No matter what you plug in for the length of the legs, you're going to get that times the square root of 2. So on your paper, if you'll notate the legs as being some random length x, and the hypotenuse as x times the square root of 2. And you see that also on the board, on the wall over there, the other triangle that's been up all year. And you might wonder, why would you leave that up all year if we're only just now getting here? Juniors, are you listening? Because next year in pre-cal, you're going to be using this all year long. So in other words, If you memorize it now, next year becomes much easier for you. You don't memorize it now, next year's a real pain, okay? We don't want real pain, okay? So, a couple of triangles that we need to have memorized.
This is the only two.
What?
This is the only two for right.
These are the only two special triangles we're going to do this year. Okay, now, what makes these special, by the way, go ahead and write this down on this page. What makes these special is you don't need to know two sides to find the third side. You only need one side to find the other two. That's what makes these special. Most right triangles, you need two sides. Use the Pythagorean theorem, get the third side. But for these triangles, just knowing one side enables you to find the other two. So anytime you're given one side of a special triangle, you can use these relationships to find the other two sides. Let me show you how it's done. Maybe on the back side of the paper. On the back side of the paper. Let's go ahead and write some things down here. Suppose, for instance, we know that this side of a 30, 60, 90 triangle is 6 inches. Go ahead and draw this picture if you would. We're going to get to that one in a minute. We're going to draw a 30, 60, 90 right triangle. Label the short leg as 6 inches. What you want to do on every single special triangle, Kendall, is label the three sides. Label the short side as x. Label the hypotenuse as 2x. Label the long leg as x times the square root of 3. And if x is 6 inches, which it obviously is, then 2x, class, would be 12 inches. And if x is 6 inches, then x times the square root of 3 would be
6 times
6 times the square root of 3 inches. And we don't have to do any math at all.
Wow.
Isn't that nice? Mathematicians are lazy. We're always looking for a way to get out of actually doing math. This is one way that gets us out of doing some math. How about this? Suppose I knew, draw a 45, 45, 90 if you would. Suppose I knew that side was 6 inches. Every special triangle, the first thing we want to do is label the sides with the letters that go with them, the x's and such. Well, in a 45, 45, 90 class, both legs get to be x. And the hypotenuse will be x times the square root of 2. By the way, memorization tip. One of them has a square root of 2. One of them has a square root of 3. Here's how I keep them straight. There's only two different measures in this triangle, right? 45 and 90. So this is the one that has the square root of 2 in it. This one has three different measures, a 30, a 60, and a 90, so it has the square root of 3 in it. Just be careful. They're not both hypotenuses. This is a hypotenuse, that's a long leg. But if it helps you remember, the square root of 3 one isn't the one that has three different things going on. This is the one that only has two things going on. Anyway, if I know this leg is x and x is 6 inches, and I know this leg is x, then this leg must be 6 inches. And if this hypotenuse is x times the square root of 2, and x is 6 inches, then the hypotenuse must be 6 times the square root of 2 inches. Easy enough?